In the xy plane, the lines x equal a and y equals b are not only basic, but fundamental to the coordinate system. When we put a bunch of these lines together, they give us our coordinate grid. Notice that the x equals 2 line is a vertical line that corresponds to all the points where the x coordinate is 2, and the y equals 3 line is a horizontal line that corresponds to all the points where the y coordinate is 3. These two lines form a rectangle with the axes, and the point 2, 3 is the corner of that rectangle. Another way to say this is that the point 2, 3 is the point that lies on the intersection of these two lines. We're going to take the same idea and apply it to 3 dimensions. Here is our right-handed coordinate grid. The point 2, 3, 1 can be found by moving 2 in the x direction, 3 in the y direction, and 1 in the z direction. Notice that the first two parts match up with what you normally do on the xy plane, and then we've added on the third movement in the third dimension. We're creating a 3-dimensional picture in a 2-dimensional medium, so we're going to help ourselves visualize a bit by turning this picture into a picture of a box. Notice that if we take away all the reference lines, it's impossible to visualize where on the grid the point is located. Again, these are the challenges of drawing 3-dimensional objects in 2 dimensions, so we'll put the box back. From this picture, we can identify the x equals 2 plane as being the plane that contains the front of the box. All the points in that plane have the property that their x-coordinate is 2. Notice that this is parallel to the yz plane, which is the plane formed by the y and z axes. We can similarly see that the y equals 3 plane is on the right side of the box parallel to the xz plane, and that the z equals 1 plane is the top of the box, which is parallel to the xy plane. The box we drew here is analogous to the rectangle we drew before in that the intersection of all 3 of these planes gives us the point 2, 3, 1. It's an important fact that all the sides of the box are perpendicular to each other. This is helpful because that means we can use the Pythagorean Theorem to derive the distance formula in 3 dimensions. Remember that the Pythagorean Theorem says that if you have a right triangle, then the sum of the squares of the legs is equal to the square of the hypotenuse. If we have a box where one corner is located at x0, y0, z0, and the opposite corner is located at x1, y1, z1, then we can use the Pythagorean Theorem twice to get the length of the long diagonal. We first apply it once to get the length of the diagonal across one of the faces of the box, and then use that length in another right triangle that stands up out of the plane. You'll need to think a little bit to figure out the lengths of the sides of the box, but it's the same concept used in 2 dimensions, so I trust you'll be able to work it out. The end result is known as the distance formula, and it tells you how to calculate the distance between any 2 points in 3 dimensions. We say that the 3-dimensional distance formula is a generalization of the 2-dimensional distance formula because we can derive the 2-dimensional formula from it. All we would need to do is set both z0 and z1 to be equal to 0, which is saying that we're looking at points on the xy plane. Once we make that substitution, the last term cancels out and we have the 2-dimensional distance formula. Recognizing these relationships helps us to see how our ideas relate to each other, which helps to better understand the material. Once we have this formula, we can use it to construct the equation of a sphere. A sphere is the set of points x, y, z that are a fixed distance r from a specific point x0, y0, z0. The distance r is called the radius, and the specific point that we're measuring from is called the center. All we need to do is convert this sentence into a formula. By convention, we square both sides of the equation because it's easier to square numbers than it is to take the square root, and this gives us the standard equation of a sphere. Again, we can compare this to the 2-dimensional equivalent, which is a circle. In fact, we can line up these formulas and see just how similar they all are to each other. Although we're not going to use it in this class, you should be able to come up with a reasonable conjecture for what this formula would look like if we had a 4th dimension. A common variable choice for that is w, but as the number of dimensions get larger, we often change our labels to being numerically based rather than using more letters. Of course, it's one thing to write down a formula, and it's quite another to try to visualize it. The idea turns out to be related to the topic of the next video, but we'll leave you to explore the 4-dimensional world on your own.